All right, let's go ahead and begin. Got an equation sheet handout and a homework set 3 handout if you haven't gotten one. We're going to be on a regular weekly schedule with the homework this point forward. So in general, you should be expecting tier 1s to be due on Mondays and tier 2s to be due on Fridays. If you're feeling super ambitious and you want to turn tier 2 in along with tier 1, you're welcome to do so. Or at any time during the week, that's fine. About 99% of you won't take me up on that, but every now and then there's somebody that's just like wants to have it done. That's cool. The pretest 1 feedback was released over the weekend, so if you haven't had a chance to look at that, see how you did with respect to everybody else, I encourage you to go ahead and do that. If you want to have some one-on-one time and go over stuff that you didn't quite understand, I'm more than happy to do that with you. Today I have office hours between 10 and noon. I've got my afternoon office hours on Wednesday as well. You're also free to make an appointment with me if neither of those times works for you. Let's see, we're going to finish off Unit 1 this week. So Unit 1 is kind of the review unit. So doing stuff that you've seen in 210 and also Chem 325. So Chapter 5 is the end of Unit 1, and so that's going to be the last content that's going to be captured on the Unit 1 exam, which is coming up in a couple of weeks. We'll have all the practice questions for that exam available early this week for you to practice with. Let's see, anything else announcement-wise? Any questions about any of this? Well, it's because we're beginning Unit 2. The Unit 2 pretest is coming due soon, so that's due this week on Thursday. Yeah.
Does that close Monday night? So it opens next Wednesday or Thursday. Does it close Monday night?
You have to check this schedule. I believe that's correct.
It says Monday, and I just didn't know it.
Yeah, so that would be, yes, that would be the last day then. Okay. So whenever the test center closes, that day would be the last opportunity to take it. All right, so before we delve into new material, we want to do a little bit of final practice with equation of state. So you did some of that for the Tier 1 homework, and I haven't done anything in Top Hat yet, so I want to try that out today. So let's see, there's a couple of questions here. I'm not doing this one. We're going to be doing that one. So what is the value of the compressibility factor for carbon dioxide at 298 K and 40 atmospheres according to the generalized correlation? So take say 4 minutes to answer that, and you're welcome to work with your partners on that. And I'm going to try and get this maximized again. Assigned. There we go. I think I might be fighting with Laura.
Yes.
Okay, who needs like 15 more seconds to enter something in? All right. So get to your best guess and enter something. All right, we'll call that good. Okay, so we had responses between the two sections, obviously all over the place. The correct answer we'll get to, and 19 of you are in that range. All right, so let's work through this. Okay, so for a generalized correlation calculation, that generally means that all of the thermodynamic properties for the fluid are going to be estimated with an equation of that form. And the Z0 and the Z1, those are most readily looked up from tables. And so we're going to be getting Z0 and Z1 from the Lee-Kessler tables. And you could also use the Abbott equations. If you're within the envelope that the book talks about, and I'll show you what I mean by that. So generalized correlations is 3.7. So 361 and 362, those are virial coefficient. Let's see, where are they? Yeah, so that's what we want. So if you don't like looking up in tables, what you can do is you can use these correlations for the second virial coefficient. And then once you have numbers for B0 and B1, you plug those into these two equations for Z0 and Z1, and then you can get a Z value that way. And so if you look at where these came from, if you actually look up the citation for the Abbott equations, it was personal correspondence between the original author of this textbook and this Abbott person. At any rate, the Abbott correlations are going to be within 2% of the Lee-Kessler tables, as long as the point that you're looking at falls within this dashed envelope. So what you would do is you calculate a reduced pressure and then reduced temperature, depending on the reduced temperature is going to depend which one of these vertical lines that you choose. So if if TR is 1.5 and the reduced pressure is 1.5, then you'd find the reduced temperature at 1.5 right here, the reduced pressure at 1.5, you're within the envelope. So the Abbott equation should give you within 2% accuracy, and you can go ahead and use those. More generally, you'd go back to the appendices, and Appendix D has the Lee-Kessler tables, at least in this version of the textbook, and we're going to look up the values that we need from there. All right, so for carbon dioxide, how does the identity of the species impact your calculation? Yeah? Yeah, I need to have two parameters to get reduced temperature and reduced pressure. And moreover, if I'm doing generalized correlations or Peng-Robinson equation of state or anything that includes the acentric factor, that's also a material property. So what are TC and PC for CO2? Thank you. What's PC? 72.9. I want to double check that because notice some of these properties been updated between the different editions. Carbon dioxide. So the eighth edition of the text anyways has a similar number, but it is slightly different. So 73.83, which I don't think is going to impact your calculation too much. Oh, sorry. So you've got atmospheres here. Cool. 73.83 bar. Good. All right. So TR then is going to be coming out to be right around 0.098. And PR is going to be either 40 over 72.9 or 40 divided by 1.01325 to go from atmospheres to bar on the top. That should actually be multiplied. No, I had it right. "40 atmospheres times 1 bar per 1.01325 atmospheres divided by 73.89, and we get a PR value 0.547. Oh my goodness. No. 1.01325 bar for 1 atmosphere. Okay, I'm done messing with it this time, I promise. Okay, we agree with those numbers so far? Good? All right, the acentric factor for CO2, that is 0.224. Okay, so at a TR of 0.98, we're going to have a table value that matches. And for a PR value of 0.547, we're going to have to interpolate. So if we go to the tables, and that'll be Appendix D. So PR at 0.98 is that row right, or TR at 0.98 is that row right here down at the bottom. Scroll that into the middle so you can see it a little better. And then our pressure is 0.547. So that is going to lie in between the 0.4 and the 0.6 range. So the two values that I want are going to be should be those two right there. 0.8398 and 0.736. Yeah, and that's what I have written down. That's for Z0. So we're going to be interpolating between two values. Z0 at TR equals 0.98 and PR equals 0.6. The 0.4 value is 0.8368 and the 0.6 value is 0.7360, and now I need to get the Z1 values. And just to save time, we have negative 0.039 for TR equals 0.98 and PR equals 0.4 and Z1 and TR 0.039 and 0.0651. All right, are we in agreement there? So these would be the values that we looked up from the back of the table. All right. So because this problem is somewhat kind and it gives us a precise lock on the row, we only need to do a single point interpolation versus a double point interpolation. So our Z0, the easiest way that I remember to do interpolation is just using a point slope formula. So point slope formula is going to be y1 plus the slope times the distance from x1. So for Z0, y1 is 0.8368. So by y, I mean the dependent value. So in this particular case, that's Z0 that I'm looking at here. So that's coming from there. Plus the slope, so that's going to be a rise over run term. And the slope is just going to be the change in Z as we march across the reduced pressure column. Remember, the slope doesn't really matter which order you do the subtraction in, as long as you're consistent between the numerator and the denominator. And then the final term is the distance from the x value corresponding to this point. So the x value here was PR equals 0.4. So my multiplying term is going to look like this, and then we put in the 0.547 right there, and we should get 0.763 for Z0, and then for Z1, we are going to have minus 0.039 plus rise over run, so minus 0.039 minus negative 0.0651, again divided by 0.4 minus 0.6, and that will be multiplied by 0.547 minus 0.4, and we should get minus 0.058 and some change. So finishing the problem off, we're going to take our interpolated value of Z0, which is 0.763, plus our acentric factor, 0.224, times our interpolated value of Z1. And that comes out to be right around 0.75. Make sense? Yeah? All right. Great. Okay, so we're going to start talking about Chapter 5 stuff now. So Chapter 5 starts with the introduction of the second law. And to talk about the second law, we also need to talk about the concept of entropy. So that's where entropy starts being discussed in this textbook. And then the physical context that the discussion all centers around is the concept of heat engines and refrigeration cycles. So, I know when I took thermodynamics, this is where the course actually started to become interesting to me, because there's a lot of physical connection between the theory that we do in this chapter and some really important things in the world around us. So entropy governs the conversion of heat into work. And that's obviously pretty important. So what are some examples in your daily life where you need heat to be converted into work to support your lifestyle, basically? So what is the gasoline for? So you're thinking automotive applications, right? Yeah, so the source of heat in your car or your bus or whatever is generally going to be gasoline. And that goes into an internal combustion engine. What's happening inside the internal combustion engine? And actually, don't answer. We have kind of a freebie top hat question for that one. So since we got up to this next question, now this is really hard to do with two sections doing it at once. How do I go backwards? Well, why don't you open up Top Hat and see if you can access if this question's active. So it says, what makes a car go? So any response is fine. Just what's happening in your internal combustion engine. And this one should be less than a minute. So take 1 minute to put in your 2 cents there. All right, that's probably good. So a lot of responses along the same lines, right? So you've got gas in a compressed piston. So you start off at high pressure, you release the chemical energy in the gas that generates heat. That heat causes the gas to expand and it pushes the piston down and that creates work. And then a valve opens and the combustion gases leave your car, and they're probably not at 0 degrees Kelvin, right? Probably a little bit warmer than that. So some of the energy that was stored in those gasoline molecules is then discarded. It's useless. You can't get any more useful work out of it. So how much chemical energy goes into the engine versus how much leaves is governed by thermodynamics. So thermodynamics places a limit on, if you were the most brilliant engineer in the world and had the greatest idea ever to make the world's most efficient gasoline engine, thermo tells you that you're not going to get any farther than this. All right, and so that's one of the first things that we can actually derive for fairly simple systems in chapter 5. So let's see. What are some other examples of where heat is converted into work? You'll have lights on today, right? So around these parts, where are we getting most of our electricity from? You ever visited the cogen facility down by Weed Recreation. It's also right behind the General Services building. Yeah? What do they do there? You have no clue how power is made. I don't believe you. Let's start with, where is the energy source? Coal, that is one of them. All right, so you've got coal. There's actually two power sources here in Ames. That's at the municipal facility actually does waste to trash, or trash to heat. It's one of the few places in the country that does that, by the way. So they had a federal grant to study the economic feasibility of that a few decades ago, actually. Has anybody ever toured that facility? No? It's kind of pretty cool because with most trash recovery operations, whether it's plastics recycling or waste to heat, the biggest cost sink is the separations problem. So trash comes in and it's already got a lot of entropy in it, right? It's a bunch of stuff all mixed together. You don't want to throw iron into the furnace. It's going to be burning the trash. It's not going to burn very well, first of all. Second of all, iron is valuable and you want to try to recover it. So you got these giant magnets that will pull iron containing things up out of the conveyor belt that has a trash feed on it. There are a few other things that they try to get out of there. They don't want tires in there. Tires create an awful lot of toxic waste when they're burnt. They try to get the plastics out for recycling. If you're in the plastics recycling game, man, that is a tough business because plastics do not like to be mixed with each other. So getting your waste stream into a pure stream is awfully hard. But anyways, that's not the worst thing in the world that you could do with your trash, is turn it into heat that you can then use to create work. At the ISU power facility, coal is kind of old school energy, and new, especially with all the fracking that it's generated a lot of natural gas cheaply over the last couple decades. Natural gas is almost free these days. And it burns much more cleanly and efficiently than coal does. So the ISU cogen, I think they're down to one coal-fired boiler, and the rest of them are natural gas boilers now. And they also have one little dinky wind turbine. That's a completely different mechanism of power generation. So anyways, these things are combustion fuels, right? So you mix with oxygen and you're gonna get a big old heat arrow. And so that's gonna make a boiler hot. And when we start to do a thermodynamic analysis of systems like this, it becomes easier to start by assuming that whatever's providing your source of heat from the hot temperature has an infinite capacitance. So you can just take as much heat out of it as you want, and the temperature never changes. And we call that a thermal reservoir. Or a heat reservoir. And what that means is that an infinite amount of heat can be taken from it without reducing its temperature. So such objects obviously don't exist, but we have great approximations of those. So a giant gas furnace is always burning new gas, and at steady state, you're taking as much heat as you need to run the power plant out of it as you're burning fuel to put energy back into it. So at steady state, the temperature is going to be staying the same. Other great examples of thermal reservoirs might be large bodies of water. So like rivers or oceans or lakes, you can dump an awful lot of heat into those before the average temperature of that body changes appreciably. All right, so that generates some heat, and we're going to say it's a QH, and it's generated at a hot temperature, TH. And that heat energy is basically just going into a boiler. There's actually going to be a boiler, and then there's going to be hot water coming out of it, and then there's going to be heat exchangers, and the actual plumbing of it is more complicated than that. But the basic process flow diagram you're going to have liquid water going into the boiler. And then you're going to have steam coming out. So it's going to be at a high temperature and a high pressure. And we're going to say it's at that TH. All right, so once you have the steam, what does the steam do? Yeah, it's driving a turbine. So you're using the steam to push turbine blades. The turbine blades do work, and that work is then further converted into electrical work. And then all that electrical work flows through circuits, and eventually we'll do either thermal. You'll be converting the electrical work back into thermal energy, which really seems backwards, doesn't it? You're starting with thermal energy, then you go through this really complicated process to turn it in to this really high value work energy, and then you go and you turn it back into thermal energy again. So that's the story of electric heating. You can also use it to store chemical energy in a battery, which then gets translated back into electrical energy to drive an electric car. So that's another example of what you can do with it. But at any rate, you're going to be generating some work. And then all the leftover enthalpy in that water as it's ejected from the turbine is waste energy, basically. So it's going to be water, and it's usually going to be a mixture of liquid plus vapor. So you can basically get energy out of steam until it starts to condense. You really don't want it condensing very much, if not at all, inside your turbine, because turbines are designed to handle gases, not liquids, and little droplets of water can really wreak havoc on the operation of a very expensive and hard to start up turbine. So anyways, that's power generation. It's really kind of the same idea as internal combustion. It's just an open process versus, well, they're both open processes, but it's easier to envision an internal combustion engine as a closed process. This could also be nuclear, right? I guess you're not burning oxygen there, though. And it could also be solar. So there are two types of solar, right? There's the photovoltaic solar, where you're using semiconductors, excited states, to capture solar energy. And then there's another way of doing it. You just actually literally use the heat from the sun to heat something. And so there are some incredibly sophisticated systems out there to do it. So one of those is on your homework, actually. And there are other similar ideas. So the idea is solar concentration. So the basic idea is you have like this giant tower of salt, and you have these robots that basically hold mirrors and point the sun rays perfectly at a target at the top of the tower, and it melts salt. Salt melts at a very high temperature, so you get extremely high values of TH that way, and you can also store a lot of heat energy in salt, and that's how it works. You get this flow of molten salt, and imagine the material science problems that you have to deal with, and you're pumping 800 degrees C sodium chloride all over the place. But anyways, once you get past this point here where you're generating the heat, it's pretty boring after that. You use the heat to make steam, you use the steam to drive a turbine, the turbine makes electricity, electricity makes us all happy. These processes also work in reverse. So if you want, you can use work to drive a compressor to compress a gas to make it hot. Once the gas is hot, you can dump its energy out into a hot summer day, and then you can take that hot compressed gas after it's dumped some of its heat energy into the hot summer day, and then you can rapidly expand it. It's going to get cold again, and then you can pump that inside through a heat exchanger in your house and suck the heat out of your house. And you can effectively dump heat from a low temperature to a high temperature. That sounds like it's backwards and it's not allowed, and it isn't allowed under certain conditions, but under certain conditions it's okay, and that's the basis of the vapor compression cycle. And so we're going to talk about all those things in chapter 5. All right, so it all starts with a statement of the second law. So the second law of thermo, very simply stated, is for any process, the change in entropy of the universe, so delta S total, has to be greater than 0. That's it. There's a special case where the total change in entropy for some process is exactly equal to 0. What this is our hypothetical reversible process. So if you can find a process for which the overall entropy change is identically 0, then whatever process you've identified is a reversible process. Now, these reversible processes are going to retain their utility throughout this discussion. And the reason for that is entropy is a state function. Okay, so for gases, so for an ideal gas, that means entropy is going to be a function of temperature and pressure only. So for some hypothetical process, if we get from point A to point B, so say it's our power plant here, and we want to do some calculations about how efficient it is in terms of turning heat into work, or for a vapor compression cycle, turning work into refrigeration. Since the entropy is a state function, we can replace the messiness of the irreversible process with a hypothetical reversible process that achieves the same state change and calculate the needed quantities from there. So changes in S are hard to calculate, for irreversible processes. But because S is a state function, the next relationship that we write down, one of the most important ones in thermo, is that changes in S can be calculated for an equivalent reversible process via this equation. So the differential change in the extensive entropy of some process is simply equal to the differential change in heat for that process and normalized by the temperature of the system from which that reversible heat either entered or exited the system. So the Q sub rev symbol that appears only a few times in the text, and it's never really explicitly defined, means just what it says, though. This is just the heat flow for a reversible process. So this equation doesn't isn't of any use to us if we're analyzing an irreversible process. That doesn't mean the equation doesn't have any utility. So anytime you see a reversible process, you're going to have an initial state and a final state. Because entropy changes are calculated by changes in states, the path that's taken from the initial state to the final state is immaterial. So if you know a way to construct a reversible path, and that's a lot of what we'll be showing you how to do between the initial and final states, then you can calculate the changes in entropy. All right, so just really quickly, we can very quickly show you why temperature flows from hot to cold using the second law of thermo as the way of proving that. So rather than this complicated flow diagram for power generation, we're going to just kind of distill down to the essential concepts here. So we're going to imagine that we have a hot reservoir at TH and a cold reservoir at TC. And we have a process symbol in the middle here. We're going to have a heat arrow coming out of the hot reservoir and a heat arrow going into the cold reservoir. So we're going to calculate the delta S total for this process. All right, so the heat arrow is going out of the hot reservoir. So that means that the entropy change for the hot reservoir is going to be minus QH over TC. The heat arrow goes into the cold reservoir. Sorry, and that should be QH over TH, the temperature of the hot reservoir. And so the entropy change for the cold reservoir is going to be QC over TC. And the second law requires that that's greater than 0. And to just make sure we're not worried about signs, I'm going to put absolute value bars on the heat symbols there. Because I've accounted for the sign by putting a minus in front of it there. So the hot reservoir loses entropy by giving heat away. The cold reservoir takes entropy by accepting heat. The hot reservoir has a larger denominator, so the entropy loss, which the universe doesn't like, is smaller because of the larger denominator. The smaller denominator at the cold side amplifies the amount of entropy that's received. So even though it's the same amount of heat that leaves the hot and enters the cold, the different temperatures make that entropy effect smaller for the hot side and lower for the cold side. So that means the only way for this equation to be satisfied is for TH to be greater than TC. And so that's really just a thermodynamic basis for why temperature moves from hot to cold. All right, so we're going to build on those concepts then on Wednesday.